Hello everyone, this is Ranjit from Cybersecurity section. Today, level 29516261 is our number. Let's get into the topic. Blast proposal for aircraft generator. Introduction. Blast cooling for aircraft generators. Discussion and authors closure of paper 44 to 81 by Eric G. Wynot presented at the AIE Northeastern District meeting. The Angeles Technique meeting, Los Angeles, Calif, August 29, September 1st, 1945, published in AIE transactions. GG Sutherland and R. Illinois Westinghouse Electric and Manufacturing Company, Illinois, Ohio. Mr. Vionet. Our electric chamber test of altitude treatments of aircraft generator brushes were taken at the specified 10 inches of water total pressure across the generator. Satisfactory performance in the chamber was not duplicated on flight test. Investigation then revealed that instead of 10 inches of water total pressure across the generator, there was only about 4 to 6 inches of water total pressure at slow flying speed. Chamber tests at 6 inches then were made and result compared favorably with the flight tests. 6 inches pressure across the generator was then adopted as the standard for chamber tests. This chamber test has been taken in the altitude chamber at the United States Bureau of Standards at Washington, D.C. Altitude conditions could not be duplicated exactly in this chamber. When the high altitude chamber was installed at Lima, equipment of duplicating altitude conditions was provided. The first objective was correlation, correlation of the chamber test data with flight test data taken by United States Army Air Forces. In order to obtain varied correlation data, sample generators were supplied from right field so that generators A, B, and C letters correspond to generators described in Mr. Wynot's paper could be tested in the chamber and the results compared with flight tests. With 6 inches of water total pressure across the generators, the result obtained from generators A and B agreed quite well with the flight test. But generator C ran much cooler than one flight test. The large difference in pressure drop in the blast tube for different values of airflow was then recognized. When an allowance was made for this in a manner similar to in Mr. Wynot's paper, the chamber test results agreed very closely with flight test results. The flight pressure was each type of generator then was calculated from the blast tube characteristics obtained from flight test and used for chamber test. The standards used for our chamber testing agree very well with curve 3 of Mr. Wynot's paper test results obtained. Check flight and results very well. His early points out the need for more complete blast tube plastics when designing and testing aircraft generators. We urge that the recommendation in Mr. Wynot's paper regarding specifications for blast tubes be followed. With definite specifications for the blast tube characteristics, both the airframe manufacturer and the generator manufacturer would know definitely what is required. The generator designer would use this information to obtain maximum output with the ventilation available. Tests could be made with the ventilation that would be obtained on the airplane. The flight performance could be predicted by test chambers which are capable of duplicating the altitude conditions. This could help prevent misapplication of generators and obtain more reliable 1944 Warren 63 electric systems. They suggest that the blastive characteristics of present airplanes and especially of experimental airplanes be obtained and made available to generator manufacturers so that they could take full advantages of ventilation available and avoid overheated and burnout generators. Harvey J. Finson, Redbridge Data OEM. Mr. Winer succeeded in greatly simplifying many of the usual concepts of blast cooling. By the use of electrical analog, he adds to a better understanding of the problems of blast cooling, especially for the electrical engineering. Judicious design of blast cooling installations should make possible an increase in pressure available for cooling of aircraft generators. This will also be evident as minimum operating Operating speeds of military aircraft continue to increase, material saving in weight for a given generator capacity, or more probably, considerable increase in capacity for a given weight will be directly result. It is possible that the paper somewhat overemphasizes the importance of the resistance of the blast tube itself in limiting the pressure available at the generator inlet. In most installations, the pressure is limited a far greater amount because of the location of blast tube inlet in such a manner as to receive only a small part of total pressure available because of the velocity of the aeroplane. The result of flight measurements on one aeroplane which has the generator blast tube inlet connected to the intercooler duct is shown by figure 1. For the most uncomfortable condition with the oil cooler and intercooler flaps open, it may be noted that of a 78% loss in airspeed pressure, the resistance of the generator blast tube itself accounted for only 5% loss. Unfortunately, examples such as this are fairly typical. In order to improve such an installation, long blast tube leading to a higher pressure area might be necessary. Then the tube resistance may become the limiting consideration. But closed and open-end measurements on the blast tube may be satisfactory for defining blast tube characteristics. The pressure for generator A, figure 2, either blast tube installation 1 or 2 would be satisfactory. Installations 1 will be far better than any generator of lower resistance. Yet this installation would be excluded by the specifics proposed by Mr. Wynett because of lower closed-end pressure. A more suitable specification would be as follows. This is the picture of orifice of generator blast cooling pressure measurements. This is equivalent generator resistance. A, B, C, D. A is orifice pressure drop transmitter and B is standard generator connector pressure transmitter connected to terminals. C is removal orifice. D is accessory compartment pressure transmitter. E is air inlet. Function design of aircraft electric actuator equipment. Instant B invest. Mr. Ganger has ably treated the factory involved in the design of aircraft electrical outdoors. Much might be gained by the interchange of ideas and information regarding design details. Gate train arrangements which allow maximum manufacturing tolerance and production methods by which semi-skilled personnel may hold their tolerances are especially to be sought. The same may be said of clutch brake design. In one actuator of recent design, it was found possible to improve the magnetic circuit and reduce the accumulation of tolerances, and yet simplify production and testing of the actuator by combining a steel coil housing, a brake face, and a quiet sleeve into one part. The coefficient of friction between the clutch faces was increased considerably by radical rather than an annular grinding of driving force. Design consideration of 400 cycle aircraft motors. W.A. Barden, Whitefield, Dayton, Ohio. This paper presents a very clear-cut picture of the requirements which have to be met not only by aeroplane designer but by the accessory designer as well. This is responsibility accessory designer to meet this requirement to greatest degree. Likewise, it 1464 is responsibility of aeroplane designer to select accessory equipment which meets their requirements to the greatest degree. The comparison of performance of a given motor on 60 cycle power with that of same motor on 400 cycle power accounts of very considerable weight saving, which is possible with high frequency power, even though certain compromises have to be made in the design of motor to operate on 400 cycle power. We still have the advantage of more powerful motor for the same weight or motor of the same power for much less weight than is possible using 60 cycle power. In order to retain the fundamental advantages of squirrel cage induction motor, it is unlikely that such devices are as a centrifugal switch will be resorted to in order to attain the best combination of starting torque, full load torque, power factor, and so forth. However, it is quite probable that these motors will be used with centrifugal clutches in order to take advantage of desirable running characteristics obtained with motor having good starting torque. It is believed that the weight saving resulting from the use of high-speed motors driving through gear reductions has been clearly established and the practice will be seen to increase, especially in the application of induction motors to aircraft. In new high-frequency capacitor, SW Zimmerman. In introduction, a capacitor for specific application to high-frequency problems, the author undoubtedly are helping to focus attention on the limitation of standard designs of component in applied to high frequency problems. Problems of high frequency bypass encountered in many places, particularly in radio noise suppression, require lower impedance devices that offered by standard rating and constructions. An early solution of high frequency bypass capacitor design in early cathode ray oscill- oscillograph measuring technique as well as in communication problems was a four-terminal network, which enabled the designer to eliminate the inductance and ratio frequency resistance of the leads or bushing to the active part of the capacitor. In general, however, for the range of frequencies considered in this paper, this design is inadequate and more satisfactory characteristics can be obtained from an exposed foil roll with double tap straps such as shown in figure 2. The axis of roll being vertical in this case. This is figure 2 a design for low inductance and high capacitance. Figure 1 is capacitor design for minimum inductance. Figure 2 is a design for low inductance and high higher capacitance. The high pass construction shown in figure 1 and 2 of the paper is a responsible compromise between these two designs but introduces two factors which may or may not be considered desirable from the design standpoint. First, the foil is required to carry power cut, and second, the effective length of the ground link changes with frequency. The first of these factors result in heating of foil and directly raising the temperature of the dielectric. The second of these factors resulting in a change of effective capacitance with frequency due to change in current distribution as higher frequencies are applied. This mechanism is consistent with author's remark in the second paragraph under the heading Performance. Figure 3. Through stud, pyranal capacitor retained 0.55 microfarad, 0.100 ampere, 250 volts maximum, alternating current or direct current radio noise separation, AIE transaction. So, thank you. This is about my